Okay, question 3 is a pulleys question. We've got 2 blocks, A and B, masses 2m and 3m, initially held at rest on a rough plane. Angle is such that the tan of alpha is 5/12. Coefficient of friction between A and the plane is 2/3. Blocks are released from rest and A moves up the plane. So there's quite a lot of information already that we can write down. Because tan of alpha, first of all, is 5/12, they don't want you to work out alpha and then find sine and cos. They want you to use the little Pythagoras Sokotoa triangle to, if alpha's here, opposite and adjacent are there, you should know the 5, 12, 13 triangle, which means we can say that sine alpha is 5/13 and cos of alpha is 12/13. That's what they want you to do. When they tell you the tan of an angle, they'll often tell you tan of an angle is 4/3 or 3/4 for the 3, 4, 5 triangle. Next thing we can do is we can add on the friction, or the force, the friction, which will be the reaction force R times the coefficient of friction. Now I can add that on because we know that the object is moving in this direction. Friction always fights that movement, or will always be in the opposite direction to the movement, and we know it's at its maximum because the block is moving. So we know that that is at 2/3 R. I can also add on the weight of object A, which will be 2mg. I can add on the tension in the string, which, because it's smooth and inextensible, will be constant throughout. I can add on the weight of object B as well, which will be 3 mg newtons. There we go. I'm going to resolve the forces from this weight here. That will be 2 mg cos alpha, and this will be 2 mg sine alpha. Okay, I've got all which means I can not need to worry about that. Now let's read the rest of the question. Find the tension. Okay, it's an 8 marker, but I've already added so much information that's going to be helpful. We should be able to resolve the forces, or just have a look at what's going on. We know that because it is moving, there's going to be an acceleration in this direction. We don't know the acceleration yet, and we also know that there's going to be an acceleration in this direction. So what we're going to do is we are going to look at the forces around B first. We know that F will equal MA, so we can say that the resultant of the forces, which is going to be 3mg minus T, so this is looking at forces down, 3mg minus T will equal M, which is 3m times A. I'm going to look at forces horizontal to the plane. parallel to the plane. that's these forces here. I know that T minus 2 mg sine alpha and minus 2/3 R are going to equal 2ma. And if I look at forces perpendicular to the plane, I know that R will equal 2 mg cos alpha. There is no movement perpendicular to the plane, so R will equal 2 mg cos alpha. That's going to allow us to find R, because we know cos alpha. Cos alpha is 12/13, which means I can write 12/13, 24 mg over 13. I've now got R, which means I can go and put that in here. So if we look parallel again, I can say that T minus 2 mg, and I'm going to change sine alpha to 5/13, minus 2/3 of this is equal to 2ma. We can tidy loads of this up. We've got T minus 10 mg over 13 minus, well, this will cancel down. We're going to have 8, so 16 mg over 13 is equal to ma. And that's minus 26 mg over 13, which is minus 2. That's helpful. And things are suddenly looking much better. We can now look back at the initial vertical movement and say that, well, we can, if I just bring that in, 3 mg minus t equals 3ma. And we've now got a pair of simultaneous equations. If I add these two equations together, the t's will cancel, and I'm going to have mg is equal to 5ma. So the m's cancel, which means I've got the acceleration. The acceleration is g over 5. I can then go back and put that into either of these and get t. So we're nearly there. T is equal to 2ma plus 2mg, but I now know a is g over 5. And if I add them together, just bring that up here so I've got some space. We're going to have 12 mg over 5 for t. If we go back to the question, that's what we were looking for. So those are your 8 marks. Okay, for part B, it then says that after B reaches the ground, A will continue to move up the plane with its residual force, but what will happen is the tension will leave the string when B hits the ground. So when B hits the ground and the tension goes, the only force acting will be the component of the weight of A, and the friction will reverse. It will have the tendency to fall down the plane. So even though the block is initially moving upwards, it will want to move down the plane. But whether it will or not will depend on the friction acting this way. Now, if this force here, which we already know is 2 mg sine alpha, if that is bigger than the frictional force, the maximum frictional force, then it will move down the plane. If it's smaller, then it won't. It will stop where it is and just remain stationary. And that's what they're asking. They're saying, will it move back down the plane, or will it remain at rest? So it all depends on whether 2 mg sine alpha is bigger or smaller than the maximum friction. We know the friction from part A. We found that along the way. Where is it? Oh, it was 2/3 of R. And we showed that R was 24. It was the 16 mg over 13. But this 2 mg sine 13 is only sine alpha is only 2 mg times was it 5/13? Let's just double check that. Yeah, 5/13. So 10 mg over 13. So because the maximum possible friction is bigger than the component of the weight, it will remain at rest. It will remain at rest. Okay, part C wants 2 refinements to the model that will make it more realistic. There's loads of different things you could say here. The best thing to do on these types of questions is go back to the question and tell you what extra information they gave you, or what kind of limitations they put on it themselves. So if we go through, we've got the fact that it was a light string. So that's one. Let's make the string not light. So that would be one thing. We've got a rough plane, so that's fine. We can't change that. We've got an angle, that's fine. We've got a small smooth pulley. So let's make the pulley rough. That would be a second change to it. The string, if they told us the string's inextensible, yes they have, so there's another one. Blocks are modelled as particles and the string is modelled as being inextensible, so we could make the string extensible. So there's 3 things already that we could say. So if we go back to the question, we can say that change it so the string the string's mass is accounted for. We could make the pulley rough, not smooth. And we could have the string be extensible. So that would make all three of those things would make it more realistic, but there are other things you could have said. I only wanted two, but any of those are fine. Like I said though, go back to the question and kind of look at what assumptions they made and undo them.